Okay, so now we have all the pieces we need to talk about polymorphism, that last big idea of object-oriented coding. Okay, so as a way of getting into that, let's kind of start with a motivational example. So let's say we wanted a list that could hold many different types of objects. What that might look like is something like a list where one node has an integer and another node has a string. That'd be pretty neat to be able to do. But currently, our list implementation can't do that, right? When we write our list node, we have to say exactly what this object is. We say, oh, it's an item, or it's an int, or it's a string. And then everything in the list has to be that. It can't be anything else. So we currently don't have this functionality. We can draw it on paper, we can think about it, we can imagine it. But up until now, it hasn't been possible with the features of the language we've discussed. Okay, but it actually is possible. We just have to work a little harder to get it to work this way. So one way we can do it is by taking advantage of inheritance. So rather than just holding one kind of specific item, we can make our list hold anything that is an object, where object is going to be some base class that we define, and then extend to be different types of data that we want to hold. And so our list will have a pointer to the base class object. And then we can put any kind of class in the list that derives from object. Now you may feel like I'm cheating a little bit here because I said I wanted my list to have a string or an int. I didn't say I wanted it to have lots of different kinds of objects. But you're right. It's not exactly what I said, but it's really close. So here's what that might look like in code. So inside list node, I'm going to say that inside every list node, I have an object star, an object pointer. And then my object class is just maybe this empty object that that's almost meaningless other than creating a name, right? So within each list node, I'm just going to have some sort of object. And then I'm going to have a string object. And so I call this class string. It inherits from object. And inside of it, I just have a pointer to a string. And then I can also have an int object. And inside my int object, the int object also publicly inherits from object. It just has an integer. Okay, so in both of these cases, string is an object, int object is an object. And that means I can put either a string or an int object in this list. And I can point this object pointer from my list node to either one of these kinds of objects. And that's pretty cool. Okay, and now in order to be able to see that I have all these different kinds of objects in my list, what I want to do is add a function override to each object. So in my base object, I'll put a print function that'll just print object because it's a plain vanilla object. And then inside int object, I'll have a print function that prints int object and then the integer that it's holding. And then inside my string object, I'll have a print function that prints string and the string that it contains. So, this is an example of function overriding because I have the same print in all of these objects, but in my derived classes, their print functions override this base class print so that when I call print, when I call print on an object, I want to see the derived type behavior, right? So that when I store a bunch of things in my list and there are all these different kinds of objects, I print out exactly what kind of object it is. Okay, so now here's what I can do. Assuming you've taken all my other list code and you just changed the list node to have that object star, then I make a few different objects, right? So I make a plain object, I make a string object, and I make an int object. In all three of these cases, I'm just using a plain object star because that's allowed. That's the is-a relationship we talked about, right? Since all of these objects are a object, then I can just use a pointer, an object star to refer to them. And then what I do is that I'm going to append to my list 01, 02, and 03, these three objects that I just created. And then using my handy iterator class, I just write a little for loop that starts at the beginning of the list and loops until the end of the list and increments the iterator each time. I get the object and then I print it. Okay, so pretty simple code. Because the object is a pointer, when I get the object, I need to use the arrow operator to call its function. Now, what's the output of this code going to be? The output of this code, what I'm hoping it's going to be, right? I appended 01, 02, 03. So what I'm hoping it's going to be is I'm going to print object, string, and then int object. That's what I'm hoping it's going to be. Okay, but actually what I'm going to get is object, object, object. Now, why on earth would that be the case? Well, why doesn't overriding work here, right? I overrode the print in each object, and I thought that when I called print on my object that I would see that overridden function. But the problem is, with the way I wrote the code, is that in every case I'm using the base type pointer. And this is a subtle case of how inheritance works, but when I have a base type pointer, all I can see are the things that are in the base type object. I can't see the extra overridden functions in the derived type. And so all I can call with that base type pointer is the print function in the base type object, which will just print that dumb vanilla object string to the screen. And what this is really telling you is that the compiler just thinks that what I have in the list are these plain base class objects. It's not able to realize that what's in the list can be lots of different kinds of objects, right? The compiler in the program just says, oh, it looks like you just have a bunch of plain simple objects. Yes, it's perfectly fine for you to stick things that are related to object into the list, but at the end of the day, they just all look like plain vanilla objects. And so I can't tell that they're strings or integers. And so when you call the print function, all I can do is invoke the print function on the base type object. So that's kind of what's happening and why we're getting this behavior. This isn't the behavior that I would really like to have. I would like to know that when I put that int object and that string object in my list, and I print out the things in my list, I want to know that I have those special kinds of objects in my list. Well, what I'm getting at here is the idea of polymorphism. The idea that from a base type pointer, from this object star pointer, if I perform an action on each of those objects, I want the action it performs to be dependent on the type of object it really is. Not dependent on the static typing in the code, which is object star. I want it to be dependent on the fact that I really created a string object or an int object and perform an action that is reflecting the real object in memory. So that's what polymorphism is. Polymorphism means having many forms. And with polymorphism, we can make each object in our list call their own print function, even though they're all accessed through the same base class pointer. What we saw before, when I ran the code and it printed object, 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 that was not polymorphism. But now I'm going to make it be polymorphic. And I'm going to make each one of those objects call their overridden function properly. Okay, and it's a very simple change to the program. It's shockingly simple. What I need is a concept called a virtual function in C++. And so what I'm going to do here is in my base class object, I'm going to say that print is a virtual function. I just need to add the keyword virtual here at the beginning. And I don't need to change anything else anywhere else in my code. All I have to do is say print is a special function. It's polymorphic. And when I call print, it tells the compiler that when we call print, we don't want it to just call this base type print, that if the object is really a different kind of object, that it should call the overridden version of print for each of those other kind of objects. So if I use a base type pointer to call print, but I'm really calling it on an int object, then somehow I'm going to jump down here and run the print for int object instead. Or if I call print using a base type pointer, but that object happens to really be a string, then I'm not going to use this one, this original print. Instead, I'm going to somehow jump over here and call the print function for string. And the compiler can figure this all out, amazingly. And it does it only if we first ask it to by putting the virtual function, the virtual keyword in front of the function we want to have behave polymorphically. Okay, so after I do this, if I take that same code I had before and I run it, yeah, okay, this is correct. So what I get now is object, string, a new item, and then int object 5. I get the behavior I want when I print these objects out of my list. Now in each case, I'm just using my base type object. But now, because I made it a virtual function, the compiler knows that I should invoke the overridden function in each of the derived classes that correspond to the real type of object in the list. And if I rearranged and had different types of objects in my list, it would still work. It's not hard-coded to this example in any way. As long as my derived type object has a print function that's been implemented, then because I labeled the print in the base class as virtual, it will go find the virtual function in the derived class and call it appropriately. So now this print really means something different depending on the object, right? If it's a string object, it's going to print string. If it's an int object, this print call is going to call print, right? I'm not always calling the same print function. I'm calling the print function associated with the kind of object that we're really pointing to. And that's polymorphism, when you get different behavior based on the object that you're actually trying to use. So inheritance gets us part of the way there, because inheritance says if a derived class inherits from a base class, then it is a base class. It has that is a relationship, and that's what allows us to call the print function in the first place, the is a relationship. Okay, but the virtual function gives us polymorphism. And it says, well, because this function is virtual, I don't just want to call the function in the base type. I want to go find the appropriate overridden function in the derived type and call that instead, right? And so now we get these nice compounding effect. We get ISA, which lets us treat all these different objects as their base type, and then we get polymorphism that allows them to have their own behavior, even though we're referring to them all in the same way. We're referring to them all as a base type pointer and referring to them all through a single function, print, but in every case, we get a different behavior. Now, there's some things that are worth noting here about polymorphism through virtual functions. So virtual functions are how we achieve polymorphism in C++. When we call a virtual function on an object, if the derived class has its own implementation for that virtual function, then the overriding derived version of the function is invoked. If there is no such implementation, then it does call the one in the base class, right? So a virtual function doesn't mean you have to override it. It just means that if you do override it, you're going to get the one in the derived class. Virtual functions are a special case of overriding. And whereas before we said overriding kicks in whenever you have the same name in a derived class, well, virtual functions only work if they exactly match in both the name, return type, and parameters. All three of those things have to match exactly for virtual functions to properly be overridden in a derived class. So it's not enough. It is not enough to just match the name. You have to match the return type and the parameters as well. And if you change them, then the virtual function overriding is not going to work. It'll override, it just won't be a virtual override. You won't get that polymorphic behavior that we want unless you make it perfectly match the virtual function in the base class. In order to achieve polymorphism, we only need to put the virtual keyword on the function in the base class. We don't need to repeat virtual in the derived classes. The virtualness of the function only has to be decided once in the base class. And then in any derived class, it inherits that virtual keyword. And the compiler knows that that function is virtual from that point on. Okay, so in summary, public inheritance follows the is a pattern. A derived object is a base class object. To give each derived class unique functionality, we use overridden methods. Okay, but overriding alone doesn't work if we use the base type pointer reference, because the base type can only see the functions in the base object. But if we want to take advantage of overriding in the derived type objects, then we have to use virtual functions. Virtual functions enable polymorphism. And it's a way of telling the compiler that when we call this base type function, what we really want is the overridden behavior in the derived type. And that way, from a single base type pointer and function name, we get the type of behavior mandated in each, we get the different behavior that we want that's specified for each derived type, right? So from a single piece of code, a single statement of code, we get lots of different behaviors. And that's polymorphism, having many forms, getting many different behaviors from a very simple piece of code.